Okay, thank you. First time I've seen that video, very professional. Okay, I'll just say a few words about our speakers this evening. John Killerby is the Chief Test Pilot at ZeroAvia, where he leads the flight testing of their cutting-edge hydrogen-electric aviation technologies. With over 32 years of experience in the aviation industry, John has accumulated more than 4,500 flight hours across 100 different aircraft types. John began his career in the Royal Air Force in 1992, where he flew Tornado, Hawk and the B-2 Spirit stealth bomber as an exchange pilot with the United States Air Force. In 2011, he graduated from the Empire Test Pilot School as a fixed-wing test pilot. His final tour in the RAF was as a flight test instructor on ETPS. He then continued to pursue his flight testing career as a civilian test pilot, working on a number of projects both at home and abroad. At ZeroAvia, John is involved with the development and testing of hydrogen electric propulsion systems to enable their goal of zero-emission aviation. He has been the test pilot on multiple test flights of ZeroAvia's Dornier 228 testbed aircraft, which has been retrofitted with a hydrogen electric powertrain to replace the conventional powered engine. Adi Wolven is the lead flight test engineer at ZeroAvia. After graduating from the University of Bath with an M.Eng in aerospace engineering with German, he spent the first 20 years of his career as an engineer in the Royal Air Force. Initially, he was a maintenance officer on VC-10, Hercules, A400M and Tornado aircraft. Then, after graduating as a flight test engineer from the French Test Pilot School, EPNA, in 2012, he completed 3 tours in 206 Squadron, including being the squadron commander and responsible for all MOD multi-engine aircraft and training aircraft testing. His final tour was as a requirements manager for the UK's Future Combat Air System programme as part of the collaboration with Japan and Italy. After joining ZeroAvia in October 2024, he is currently focusing on future integration projects on the Dornier 228. Welcome.
Thank you.
Very much looking forward to your speech. Thank you.
Good evening, everybody. It's nice to see some familiar faces. As Mark says, I'm John Killerby. We're going to start off by showing you just a short video to whet your appetite and show you what we've been up to in our recent test campaign. We'll then go on to talk in more detail and would like to take questions from you at the end.
Tango, contact tower, will make it 5 Quebec. Final line at 1.
You ready? Doors and windows, door lights out. Takeoff brief is complete.
Zero Alpha, runway 26, the wind 320, 5 knots. Take off your discretion.
Temperature's good.
Temperature's looking good.
Zero Alpha is downwind full stop at level 2,000 feet. Zero Alpha, full final, number 1.
120 knots.
Zero Alpha, runway 26, land your discretion to wind 280 at 5 knots.
This is still really good. Voltage has gone high with 790 reducing.
so hopefully that has whetted your appetite. And this evening, this is what John and I will take you through. First of all, why we as a company are working on hydrogen electric. Then some of the technology behind that powertrain, principally how a hydrogen fuel cell works. And then how John and the team took that forward to that first flight that you've just seen in the video. And then I'll talk about how we progress that into a commercial future. So first of all, why hydrogen and electric aviation? Well, I guess the world is faced with that competing argument that aviation has got huge societal benefits, quite neatly kind of summarised there by Bill Gates. But on the flip side of that are massive environmental and sustainability side effects. You can see there in the graph that it's predicted that the use of aviation increases almost exponentially between now and 2050, but that drives a 25% increase in CO2 from aviation, whereas the world's intent is to drive those CO2 emissions down to net zero. So it feels like that we are at the kind of threshold or the birth of the next aviation age, where the comet ushered in passenger jet aviation for the masses, but now the world and our small part in it needs to take that on and make that sustainable so that everyone in the world can experience the benefits of aviation. And of note, only so far 10% of the world's population have flown in an aircraft, so you can see there's a real driver for that increase in the use of aviation. So that's the problem set. Now we in ZeroAvia have focused on hydrogen, and in a minute I will talk about how that fits into perhaps the broader green or net zero solutions. Now, hydrogen, as you all know, is abundant. So unlike fossil fuels, which we're going to run out of, 75% of the universe's mass is made up of hydrogen. It's got 3 times the energy density of a jet fuel by weight, but the problem with it is in its gaseous form, it's very low density, and that means that in, for example, those test flights, we had to store that hydrogen at 350 bar. That drives a large tank in terms of the strength you need of that tank, and thus the size of it. You really can't generate high pressures without significantly having a much larger and uneconomical tank. So we can use hydrogen, but it takes up a lot of space in gaseous form. Maybe liquid hydrogen is the solution, but one of the troubles with that is its boiling point is minus 250 degrees centigrade, so that brings in a whole host of how do you store liquid hydrogen, how do you produce it, and how do you then use it in an aviation context. All of those problems will start to unravel, hopefully, during this presentation. And I kind of like to think those problems almost make hydrogen seem impossible compared to how we use kerosene or fossil fuels today. But if you flipped it around and imagine we've been using hydrogen for the last 100 years and found this new fuel source, kerosene, you'd go, well, the thing produces a lot of CO2, it produces a lot of nitrous oxides, it produces particulates, we're going to run out of it. When it leaks, it causes environmental damage, and it's hard to sweep up, and it ignites. We have had problems with being icing in fuel tanks or leading to fungus in the fuel tanks, damaging the aircraft. And they're all technical problems with kerosene that the world has generally solved. I believe that these hydrogen problems are also ones that can be solved. And on the plus side for hydrogen, it it's easy to get hold of. When it leaks, it rises, so it actually escapes quite quickly, and it doesn't generally pollute when it leaks. We've got to manage in a different way to how we managed with kerosene, that it's very easily combustible, i.e. in a wide range of hydrogen mixed with air leads to combustion. You see there between 4 and 82%. Likewise, it's very easy to ignite it. So when you feel the force of static shock on your finger, you need half of that energy to ignite hydrogen around you. And its flame is invisible, so we need other solutions like ultraviolet and infrared sensors to sense fires. So that's the challenge in front of us, but the reason why hydrogen, I genuinely believe, has got a key role to play in that kind of portfolio of green solutions. And I think this slide is more useful to look at the different options. Don't quiz me on my building of pie charts, please. But we've got hydrogen electric, which is the ZeroAvia solution. That drives quite a bit of weight in it at the moment, and John will go into that powertrain shortly. And we need to work on solutions for how you can store it in the smallest volume possible. Another problem is we generally store aviation fuel in the wings at the moment. Those wings, you can't store gaseous hydrogen or keep liquid hydrogen cooled in. So we need to store our hydrogen fuel in a different part of the aircraft. Next one is you can combust hydrogen in turbines, for example. That does reduce the CO2 emissions, obviously, but you cause other non-CO2 impacts, such as contrails and generating nitrogen oxide fumes. And you need to consume a lot of hydrogen, so you need even larger fuel tanks for that. And we've got battery electric, and there are certified training aircraft out there, the Pipistrel Velus, but with current battery technology, such as lithium ion, it's heavy, so you really can't upscale that battery technology into larger aircraft. And in my previous role, we flew the Pipistrel Velus electric aircraft, the two-seat trainer, but with that battery technology, you broadly got maximum of a 30-minute training flight out of it. So not yet at the matching aviation fuels performance. Then there's sustainable aviation fuels, which, depending on how you make them, could be lower in CO2 or could be net zero. But we've got to find a feedstock from somewhere, and is that feedstock, in terms of biomass, for example, sustainable? And if we're going to make it purely synthetically, we need hydrogen to mix with those hydrocarbons to make the right hydrocarbon length chains. So if you're making hydrogen anyway for that, then it's more efficient to use that hydrogen for, let's say, hydrogen electric or hydrogen combustion. And finally, at the bottom, you've got that combination of using hybrid electric. But that has a small impact, small benefit to the climate. And I think you can see that probably all those solutions have a role to play, whether that be long-term or in the short term. It probably is very viable that the short-term solution is that SAF usage, in my mind, potentially 10 to 20 years. But in parallel, we need to be working up our hydrogen electric solution. And as you'll see, we'll start at the smaller scale in the regional type aircraft, which allows you to get the technology working and then allows you to develop the scale as we go forward. So I'll hand back to John to talk about how fuel cells work. Oh, sorry, I've gone the wrong way. Classic.
Thanks. I'm going to caveat this with I'm a pilot. I'm not a physicist or a chemist, but that means it's going to be a simple explanation. So the working principle of a fuel cell, fuel cells have been around in technology in other applications for quite a long time. We're using a proton exchange membrane type of fuel cell. It has a polymer and electrolyte catalyst that essentially separates the proton and the electron from the hydrogen molecules that enter at the anode. That electron is then used by us to generate an electric current to power our motors and turn the propeller. The combination on the other side with oxygen creates the byproduct of heat and water. We put 455 of those cells, combine them in a single module, and that will generate around 400 to 1,000 volts of direct current at about 120 kilowatts. So it's a building block approach, multiple cells combined in what we call a fuel cell stack. We have to supply the hydrogen. As Adie's already mentioned, it comes from a gaseous form in a tank inside the aircraft. We provide oxygen to the cathode of the fuel cells, and that's provided in the form of compressed air. So that is compressed by a compressor similar to a turbo on a car engine, and is fed in at the correct partial pressure of oxygen to generate the chemical reaction. That electricity is then dealt with through cabling to inverters that convert the electricity to AC current to drive the electric motors. The testbed aircraft that we're flying, and I'll talk more about that in a bit, includes 4 electric motors and 4 inverters, and they have a direct drive to a propeller. Obviously, the 2 byproducts that are mentioned from the chemical reaction are heat and water. So we have to deal with that within the fuel cell system, and we include what we term a balance of plant. That includes the compressor, conditioning for the air going in, removing any particulates that may be in that air, compressing it and feeding it into the fuel cell. And on the other side, the hydrogen management is taking the gaseous form inside a tank that's in the fuselage through a pressure reduction down to around about 7 bar operating pressure that feeds into the fuel cell. The byproduct of heat obviously has a significant byproduct. The fuel cell operates at a temperature, an optimum temperature of around about 68 to 70 degrees. That means that the water is coming off and very, very soon is forming a liquid form, and that's evacuated through an exhaust pipe under the aircraft, and you'll actually see that in a short video later. And the heat is removed from the system by a liquid cooling system, much like you'd have in a car with the radiators, and airflow through the radiators on the outside of the aircraft, cooling the system, keeping it at the optimum temperature of 70 degrees. Our total infrastructure, looks something similar to that. You can see the motor and inverter unit at the front, the fuel cell stacks with balance of plant. The current system that we're operating weighs around about 190 kilos. It's nominally 600 kilowatts. At the research and development phase, we're generating around about 400 kilowatts of usable power, but our the first product, the ZA600, will be operating up to 600 kilowatts, which will give us around about 250 mile range with 90% emission reductions. Don't obviously have the noise of a jet engine, but a lot of the noise is still generated by the propeller, and we estimate a 40% reduction in operating costs. So the development and the proof of concept aircraft is important to note, and this may appear a slightly more simplistic slide. You can tell which one I created. The test aircraft, in terms of our redundancy, we've got two 455 fuel cell stacks that generate around about 120 kilowatts each, and we've got a set of batteries that will generate an equivalent power. So in terms of redundancy for our flight test campaign, we've got two of the motors that are powered by the fuel cells and two of the motors that are powered by the batteries. The reason for that was there was an input from the regulator very early on that because this was new and novel, they wanted to have some form of redundancy. Essentially, because of the choice of aircraft that we're using, we've got the turbine engine still on the right-hand side. So from a test and development program, the aircraft is safe to fly on one engine, but we've got that further redundancy. The important thing to note about this, and the reason that I want to talk about this slide in particular, is because if you look at the total weight of the fuel cell systems, including the tank, we're for the same amount of flight availability and power generation, we've got over double the weight of batteries to provide the same amount of power. So the battery weight at the moment is 900 kilos, and the fuel cell weight, including the tank, is around 450 kilos, and that's with 5 kilos of hydrogen. So that kind of puts into context a little bit the figures that Adi was talking about earlier. So we've put that into a Dornier 228 aircraft. It's a fairly old platform. The aircraft that we're flying was built in 1985, but it has incredible single engine performance. It's actually possible, although not certified, to take off from a standstill on one engine, and that, although not required for our flight performance, that is an amazing safety factor to have during flight test campaign. There is a playoff effectively between cost and availability. There are a number of other aircraft that would be equally good. Twin Otter is a great example, but the net cost of the aircraft compared to the operating cost is a significant factor for us in a startup company. And we've got a very good useful load, so we are able to carry 2,000 kilos of weight. That's the aircraft. You can see I talked about the cooling effects. We've got two of these ducts on the outside of the aircraft. You can't see the other one. We've got our electric powertrain on the right-hand side, and you'll notice there's a slight difference between the propeller design. This is the legacy turbine with a 4-bladed metal Hamilton prop, and on the left-hand side we've got a composite 5-bladed MT propeller. You can't quite see from this picture, there are further ducts on the outside where the airflow comes out, and actually this window here has been removed and is a wire gauze, and that's part of our safety mitigation to enforce an airflow through the cabin to mitigate against any possible hydrogen leaks. So inside the aircraft, in the picture on the left, that is looking from the cockpit to the rear. You can see the hydrogen tank. As we've said, that's 5 kilos of hydrogen in gaseous form at 350 bar. We've got the 2 stacks of batteries. They're lithium-ion LiFe phosphate batteries. And right at the back are our 2 fuel cell stacks with balance of plant. Other notes, we've got these fans at the back in the bulkhead, and that's part of the that withdrawal of the airflow. So we're keeping an airflow through the cabin to mitigate against any possible leaks. We've also got detection systems that are, you can't actually see them, just about there, and at the back. On the cockpit side, it's a bit of a Frankenstein's monster. We've got the conventional instrument displays, right-hand engine displays. We've removed the left-hand turbine, and we've got a traffic light system, warning lights for leak detection, fan stoppage if one of the fans fails, and an open circuit voltage, which is essentially a heat sink, which is used in routine operation to draw current from the fuel cells during startup. If you turn the fuel cell on and it starts to generate, i.e. you start feeding the hydrogen into it, the voltage will go up if there's no current draw. So to keep the voltage inside the limits of the inverters, we feed that into it's essentially an electric heater. And that takes away that initial energy until we can start spinning the propeller. Here it is in a little bit more detail. On the right-hand side, press the right button, we've got a tablet display. That gives the flight test engineer a little bit more information, in particular about the temperatures, operating temperatures of the fuel cells, so that we can keep them within the limits. We've got the pilot's display, which you saw in the previous picture, and you'll see that in another video and the next slide. Controls for the high voltage power. You can't see low voltage power controls, but they're just down here. And that's me. This display is if anybody's into motor racing, you might recognise it. It's an automotive type display that's been customised to provide control information for the electric powertrain and associated warnings that might be associated with operating it. Essentially, from a pilot's perspective, control of the electric powertrain is a torque control. So we'll demand per leg around about 800 newton meters of torque during the takeoff roll, and then we'll have a max continuous power of about 750 newton meters per leg. So that's at the maximum power rating of 120 kilowatts per leg. So we started our ground test campaign with a series of bench testers, and the aircraft was delivered to us in November 2021. We went through commissioning and ground testing before our flight test, first flight on the 19th of January. So from flash to bang, a very, pardon the pun, a very fast and rapid integration into the aircraft. We use a lot of a lot of the existing technology for fuel cells, the experience for that, and electric powertrains comes from the automotive industry. So we have integrated a lot of automotive expertise into a new and growing aerospace company, and that comes with certain challenges. We've looked at the preparing not just the aircraft for flight test, but preparing the team, getting a group of very clever and motivated people to understand the aerospace aspects and the importance of safety and understanding the known unknowns into a test campaign. And part of that was the ABC of testing, that assume nothing, believe no one, and check everything. You've got to have that rigour throughout that programme, which is the importance of bench testing, ground and commissioning and ground testing before you then go to do your successful first flight. This is an example of one of the early ground tests. This is the first fitment of the fuel cells into the aircraft. You can see a little bit more detail. Most of this is the plant of the fuel cell. This one is end-on and this one is side-on. The conditioning for the air takes up the majority of the space within there. The actual fuel cell you can't see, but it's just a small kind of battery-sized device at the bottom. It looks fairly rudimentary, but essentially once the fuel cells were in and were commissioned, there was we needed to have pipes running out basically to get get rid of the electricity that they're generating, because we weren't sending that to a motor at that point, and that goes into a load bank. So the cables that you see there are all going off to load banks. So this is low power testing, but it's that first commissioning run of the fuel cell. I took this video with my phone, so I do apologise for the quality. That's the exhaust there, where the water vapour comes out. And I think the important thing from a flight test perspective is to understand as much as you can on the ground, because on the ground it's ground zero. Once you get airborne, there is you don't want to be discovering new things in the air. Our first flight, as you've already heard, was on the 19th of January 2023. We've done 13 flights since then. The last flight for us was in April of last year. I'm going to play a video. There's a lot of it's quite loud, so I apologise if it's too loud. Some of the things to look at is that first run-up of the fuel cells. The conversation you hear between me and James Yap, who was the flight test engineer on these flights, is about fuel cell commissioning. It's getting that fuel cell up to the operating temperature of 68 degrees and making sure we've got they're like thermostat valves within the cooling system. You want the system to warm up as quickly as you can, and once it gets to the operating temperature, you don't want it to get too hot, so the thermostat valve opens and you get a flood of cold coolant going into the system. We see a temperature drop, and that's when we talk about this three-way valve that's beginning to open. that's our indication that the fuel cells have got to the operating temperature that they need to be at, and the three-way valve is opening, so we know we're getting that flood of cooling. I'll press that.
50%.
Victor was in hold position.
696.
Victor, hold position, there's a short delay.
Both relays are open, but they are currently closing, so you should be able to run at power now. I think we're bouncing to a nice open position.
Right. I'm going to bring the turbine up to 60.
Zero Alpha, runway 26, to wind 320, 5 knots, take off your discretion.
Everything's set.
Three valves are good.
P's and P's on the turbine look good. 60 torque.
Kemble, Golf Bravo, Charlie, uniform.
Thrust looks good. Temperature's good. Freeway valve's good.
Three-way valve's good.
Number 26 left hand.
Minute 34.
QFE is 992 hectopascals. Pass your message. 26 left hand, 992, 7 miles to run for join and land. Okay, you to the north of Kemble, are you? FM, we're approaching Cirencester. Okay, can I just ask you to remain outside the Kemble ATZ for the moment?
92.
Testing in progress due to the node.
105.
Orbit Cirencester at 3,000 feet. Thank you, I'll call you shortly. How long?
Positive rate. Committed.
6 minutes in most, I should think. No problem.
And so that's the takeoff of the first flight. As I said, we've done 13 flights since then, and a lot of that program was to expand the envelope up to 5,000 feet and explore the speed range. But it's a fixed pitch prop, so the faster the aircraft goes, the higher the RPM and the less power you can put through it. So all of our flights and our optimum speed to fly around the pattern is at 120 knots, because that's the optimal blade angle of the propeller. I'll hand back over to Adi for a discussion on next steps.
Yeah, so that has shown our prototype technology and kind of proof of concept. Here is kind of what we need to do next in order to make it applicable to these types of aircraft. And I sit with the designers each day. Lots of these problems are solvable. They just need resource and time applied to them, in my mind. So we are targeting, first of all, a motor, which is an evolution from our prototype 1, which would be a small turboprop called the ZA600. That uses gaseous hydrogen because that's the easiest one to produce, the easiest type of hydrogen to store and consume on the aircraft. And we use the fuel cells that John has just talked you through. That allows us to then progress first of all to what is there as a high temperature fuel cell. That means that proton exchange membrane in the middle of the fuel cell, which takes the oxygen and the hydrogen. Currently, that works at an optimum temperature of 68 degrees centigrade, which needs a lot of plant to manage that cooling. But high temperature proton exchange membrane fuel cells can work at 100 degrees plus. That immediately reduces the amount of cooling you need to do, so that saves you space and weight and the power for cooling. And also, that waste product of the water is now at greater than 100 degrees centigrade, so it's in a vapor form, so it's easier to manage and to remove away from the fuel cell and discharge overboard. That's harder doing with liquid water. As you'll see, when you get beyond those small commuter aircraft, you really need the extra capacity that a liquid hydrogen tank gives you. So you'll see that anything beyond those small aircraft like a Cessna Caravan, you really need to get into liquid. Again, this picture just paints, whilst we are busy getting a certified powertrain certified, in parallel, technology needs to be advanced with things like liquid hydrogen tanks and those high temperature proton exchange membrane fuel cells. And the way we're getting after that is ZeroAvia purchased a company based down in Sandwich in Kent, and those staff have now moved to where we're based at Kemble in Gloucestershire, and they are doing R&D now on those high temperature membranes. John's talked about the whole fuel cell comprises in the region of 455 individual cells. Right now, the team at Kemble are doing testing on those on individual fuel cells and are progressing on a daily rate. Liquid hydrogen tanks. In a minute, I'll talk about what we've got planned for the rest of the year with flight testing with liquid hydrogen. But in parallel to that, we have UK government funding to develop liquid hydrogen tanks designed and manufactured in the UK. We're doing that because the current liquid hydrogen tanks are not large enough in terms of capacity for those larger uses. Cool. So on to liquid hydrogen. So we are this year going to conduct ground and flight tests with a liquid hydrogen tank. It's essentially the same powertrain that John has described, but we remove the gaseous tank and replace that with a liquid tank. It's not quite so simple as unscrewing the tank from the floor and putting a new tank in, because it's quite a big weight and balance change. So literally the whole internal layout of the cabin is altered. So that photo that John showed is very different. But you can see that this company here, H2 Fly, they flew, this is a 550 kilo pipistrel aircraft, and they did 4 flights with liquid hydrogen in 2023. That's them flying in Slovenia. That's them on the Air Liquide test stand in Grenoble, France. That tank contains 16 kilos of hydrogen, so it's broadly the same, takes that same volume as the gaseous tank. The gaseous tank stores 5 kilos, this stores 16 kilos. So you can see, even with an early prototype tank, you're getting significant increases in that storage capacity. So we'll be testing that tank, and that's a 550 kilogram aircraft. The Dornier weighs in at about 5,700, so it's about 10 times larger aircraft powered by the same quantity of liquid hydrogen. So the benefit of us doing that is we'll be the largest aircraft to fly with a liquid hydrogen tank. So we'll really challenge the mass flow rates you can extract from the tank. And one of the key challenges is that liquid hydrogen is stored at 20 degrees Kelvin. The fuel cells need to have the hydrogen at between plus 5 degrees centigrade and about 40 degrees centigrade. So you have to heat that liquid hydrogen, turn it into gas, and then heat it again to get it up to plus 5 degrees centigrade. And what we use is that waste heat that the fuel cells generate, that we have to use cooling to manage. We now use that byproduct waste heat, and we use that through a heat exchanger to condition that liquid hydrogen into the right temperature. So it's the first time we've kind of taken one of the disadvantages of fuel cells and used that waste product in a kind of symbiotic fashion. So Our Dornier aircraft at the moment is stripped out. The tank has arrived at Kemble, and our engineers are doing the fitment of that tank to the aircraft. And I've talked about one of the challenges of liquid hydrogen. The other main challenge is that even with the best vacuum tank in the world, you're still going to get that liquid hydrogen boiling off and producing hydrogen gas. That's okay when you're consuming the hydrogen gas with the fuel cells running, but when you're storing the aircraft, that gas is boiling off and the pressure slowly increases in the tank. So both the Pipistrel aircraft and our Dornier, we've fitted vent lines which will, imagine we've refueled the aircraft and waiting to go testing, you'll get a very slow flow rate of hydrogen going through those vent lines and departing the aircraft. You need to put that hydrogen, or you need to vent that hydrogen away from the aircraft in the safest place. And we do that by having vent lines that run from the tank in the cabin all the way up to the top of the tail at the top of the fin. So furthest away from humans, ignition sources, and can vent upwards as it's more buoyant than air. So we've done that hydrogen that's venting off is still quite cold. So we've done modelling to understand how that might cause icing on those vent lines at the top of the fin. And some of our early ground test points will be testing to see that that model of the icing matches reality. And they're all key test points in understanding how we manage hydrogen aircraft when they're fully in service. There's plenty of other challenges out there, but generally one by one our engineers have been tackling them. And that liquid hydrogen tank also plays into the long-term future. This is one of the models of the Airbus ZeroE project, and they had a ZeroE program with doing modelling and simulation with a turbofan hydrogen-powered aircraft, a turboprop, and a hydrogen-powered electric fuel cell aircraft. And I know it was in the news that they've delayed their kind of entry into service for that ZeroE project, but nevertheless, they confirmed this year that the best long-term solution is that hydrogen-fueled electric powertrain. So that you can imagine that at some point our technology will converge with that longer-term Airbus vision. And that is tangible liquid hydrogen testing that we'll see this year in the UK. If I leave you with one final kind of sort of thought to take away, is we've talked about how we'll mature the powertrain, and our first applications, once it's certified, will be retrofitting that to existing aircraft, like the ones you've seen throughout the presentation. But ultimately, once the technology is proven, that could herald in a new threshold of how you design aircraft, because, as I said earlier, no longer are the wings a good place to store kerosene. You need to store your liquid hydrogen fuel in tanks that are the best shape for it. So these are some of the simulations that people have done. First of all, with Airbus ZeroE, with that kind of blended wing concept. So that is maybe a better internal volume for storage. And again, one of our kind of ZeroAvia mock-ups of how aircraft design may evolve dramatically off the back of that. That concludes our presentation. So more than happy to take any questions that you've got. Thanks.
One question, you had a slide where you talked about the battery being redundant.
I think that was in our prototype, wasn't it?
Okay, so in the 13 flights, I'm not an engineer, I'm just a dumb banker. So you talked about the battery is redundant, but was the battery in operation with the hydrogen?
Yes.
Or was,
So
was it ever hydrogen alone?
In our R&D testbed aircraft that we've flown so far, the batteries are there as a redundancy measure. So we've got two legs working in parallel. In the next iteration, we will remove the batteries, and all the power will be generated from a bigger fuel cell stack to power the electric powertrain. The batteries are there largely on an insistence from the regulator to give us a redundancy in a technology that nobody in the regulator really knew very much about. That they work very closely with us, and they are working alongside us to understand the technologies a lot more. So we have a very good relationship with them. They've got very interesting programs within the regulator now to work on hydrogen technologies. So it's part of that building block approach, really. As I said, they weigh a lot more than the fuel cells and the fuel tank. So for us, getting rid of that is really important, because it will allow us to carry more hydrogen, more fuel cells and fly along.
Yeah, and just to add to that, that last point, the range and duration of your previous test flights have always been limited by the batteries running low on power, rather than the fuel cell hydrogen, isn't it?
Yeah, so the aircraft, the design initially was designed to match the duration and power output from the two legs, so they are evenly matched. But actually, what we're seeing is as the batteries are used and get older, whilst they still are sufficient to power the two legs, they are the limiting factor. And we, because of thermal stability in the batteries, we don't want to operate them down to a level much lower than about 35% state of charge.
And so when do you expect to fly purely on hydrogen, one engine then, without the battery? Because that'll be with the liquid one.
That'll be, yeah, but that would be gaseous hydrogen, a fuel cell system in a Cessna Caravan, so in a single engine aircraft. The Dornier will remain as a two engine with a turbine engine on the right hand side to allow us to accelerate our test campaign whilst maintaining redundancy and the safety factor for the turbine engine. We've actually got another Dornier 228 that will be our second testbed aircraft to allow us to leapfrog the test program faster than we would be able to do with one aircraft.
Thank you.
Hello, thank you. Very exciting lecture. I'm Dr. Young from Cranfield University. Yes. Two questions for what's the total power you mentioned for the Dornier aircraft with your fuel cell power plant? Is it 600 kilowatts?
So the aircraft that we're currently flying, or the next iteration that's going to go in the second testbed aircraft?
Okay, so 600 kilowatts.
So the existing design is that we're flying at the moment, or we'll be flying again soon,
Yeah.
is 400 kilowatts.
400
Yeah.
kilowatts.
And the certifiable version of that will be 600 kilowatts.
Okay, okay. And for that 400 kilowatts, how much thrust you are generating?
We're generating about, well, the turbine engine is 533 kilowatts
Yeah.
of power. We're generating 400 kilowatts. It's an
Right.
equivalent torque of about 60% of the turbine.
Okay, okay, thank you. And for the following question to that is, why choose the left engine as the replacement rather than the right one? I suspect that's related to the critical engine selection. here?
Yes, it is. So the aircraft itself, a failure of the right engine is critical.
Right. Okay.
In the conventional aircraft,
Yes.
because the prop blades are going
Counterclockwise.
downwards on the left-hand side,
Yes.
on the outboard side.
Yeah.
So the yawing moment from the left engine at full power of the conventional aircraft is
Yeah.
higher.
It's higher. Yes.
However, if we want to reduce VMC to a minimum,
Yep.
if we change the left-hand engine,
Yep.
the downgoing blade is on the inside of the right engine. So the yawing moment is actually less.
Yep.
Coupled with the fact that it's a fixed pitch propeller, the prop windmills,
Okay.
and the drag that's created by the windmilling prop of the electric powertrain
Mhm.
is less.
Okay.
So that reduces the VMC by another factor,
Okay.
and
Yeah.
actually at the weights that we're flying at, our VMC is reduced to a point where the aircraft will stall first.
Oh. Okay. Yep.
So we don't have a handling control issue at
Yep.
minimum speed. It's actually below landing speed. So it's,
Oh, that's good.
we're never really going to get there in that, and that's one of the reasons why this aircraft is a good choice to use.
Thank you very much.
That was quite technical. I'm amazed I remembered it.
Good evening.
There is one gentleman here at the front that's had his hand up all the time. So, hi.
Thanks for a great presentation. In a steady state production environment, with the system installed to let's say a nominal 19-seat aircraft, would you expect the payload penalty to be either full passengers or just on a weight basis?
So, in terms of a 19-seat aircraft, because the 19-seat aircraft is the R&D prototype test bed. From a point of view of a 9-seat or 11-seat aircraft, there will be a reduction of about 40% in the payload, because you've got space for the hydrogen and you've got the fuel cell stacks and the balance of plant. But you know, there's a penalty at the moment in the development of the technology that for green and truly zero emission aviation, in my opinion, is worth it. Rome was not built in a day.
Thank you.
And sort of, if you did a Cessna Caravan modification, for example, it's got an additional belly pod you can add. It would be that kind of area that we'd put quite a bit of that hydrogen powertrain into, like the tanks, for example, to not take up all of that cabin capacity.
Yeah, I'm just thinking in terms of, once you want to sell it and commercialize it and make it attractive to the financial community. My friend in front here
Yeah, so
will be looking at that. Thank you.
Pleasure.
definitely got to go, yeah.
Now it's going to be
Thank you very much for the lecture. Your takeoff weight and your landing weight, is there a difference? And is there a new concept in weight and balance?
The takeoff weight, obviously from hydrogen usage, we're only using in the testbed aircraft 5 kilos of hydrogen. We're using an equivalent weight for the same flight of about 200 pounds of jet fuel. So there is a difference, but in the final certified version, there will be a small delta in weight, which changes the way of thinking for operators. You know, if you scale that up to a large scale, then in the pictures of the types of aircraft that Adi showed at the end, then you're talking a significant weight change, but about 3 or 4 times less than you would see in a jet aircraft.
So I'm interested in the efficiency between the amount of energy stored in the hydrogen versus the power output from the engine. So you got a ballpark efficiency figure?
I have got a ballpark figure, but I would rather check it before I tell you what. If I say it's in and around the 10 to 15% at the moment, I'm not 100%. I would want to check that before you went away and said.
My guess was about 20%. And a follow-up question is obviously
What's your guess based on? What's your...
just on sort of just basic efficiencies between sort of combustion engines.
Well, yeah, this side of the technology is very different. There's a slight loss in the compressor because it's electric. Mm-hmm. There's a slight loss in terms of heat, but really there isn't the same losses in a hydrogen electric in the fuel cell system that you would see in a conventional engine.
So obviously the key to the future is scaling up liquid hydrogen storage. So have you sort of extrapolated that out to actually if it's feasible or not?
Yeah, I think we as a company, I think you start small with those commuter aircraft, which then get infrastructure at airports, which you can scale up. I guess it's a bit like the Tesla model where you've got to put the car chargers in place whilst you're building the cars. There are various grants that the company have also used for example, making or optimizing liquid hydrogen tankers, the same size that Esso or Shell drive around fueling. Now those tankers already exist, but they're not very good at recycling the gaseous hydrogen that's boiling off and recondensing it back into liquid hydrogen. So trying to make the ideal tanker has been a project other parts of the company have worked on. One of the issues with that is obviously liquid hydrogen is 20 degrees Kelvin. The speed of sound is quite slow at 20 degrees Kelvin. When you pass those bubbles of gaseous hydrogen back into the liquid, if you don't do that in the right fashion and do it too fast, they're close to the speed of sound and you create sonic issues in your tank. So I think that solves the kind of getting the hydrogen to the aircraft. I think how you make green, sustainable hydrogen is a challenge not just for the aviation industry, but for other parts of the chemical industry. You kind of got to drag that demand, I think, with the aircraft.
Yeah, and I think on a practical sense of actually scaling up the fuel tank to carry liquid hydrogen in an aircraft, you might find the solution is different to what we would conventionally think of in scaling up the fuel tank size. You might find that there are multiple smaller tanks because it manages a certain aspect of the qualities of liquid hydrogen, stratification within the tank, temperature differences and mixing effects. That's why we're doing this.
Yeah, or you might find that you have sort of cassettes of liquid hydrogen tanks, and as the aircraft lands, you drag out the empty tanks, and you've got preloaded new tanks that you insert into the aircraft.
Yeah, you could extrapolate all this at the moment quite easily, with the back of the fag packet type calculations as to whether or not it's practical or not. So I guess the question is, have you done those calculations and is it actually practical for commercial aviation?
Well, I'm the pilot, I haven't done them, but the company is looking at that and they've done that to a level that we're convinced or we are satisfied that there is a future. I think the future for liquid hydrogen, although we're looking at flying on liquid hydrogen this year, the future for commercially viable liquid hydrogen is significantly further in the future.
Hello. Two questions, if I may. So, firstly, have you got any support from the type certificate holder of the 228? And secondly, I am amazed nobody else asked it. The fixed pitch prop. I assume that's because there's no oil to squeeze through a governor. And is there an in-service solution for that eventually?
I'll answer the second question first. The reason for the fixed pitch prop is this is a start-up company, it's rapid prototyping, and we wanted to demonstrate flight as quickly as we possibly could. We developed from delivery of the aircraft to ground testing to flight testing within just within a year. So the complexity of a wobbly prop with the associated oil control would have probably delayed that significantly more. The next iteration of the design and the next aircraft will have a wobbly prop and feathering capability, and obviously the certified design will have that. And just remind me what your first question is.
Well, just on that, will that be, because obviously, you know, my normal head says oil-based, will that be an oil-based system, or will it be some clever electric-based system?
It will probably be oil-based, because we aren't a company that designs prop mechanisms, and there aren't many companies that have an electrical control for a prop of that size, unless you are one of them.
Sadly not, no. And the other one was just whether you have any support from whoever is the Dornier 228 type certificate holder at the moment, the sort of the OEM.
That's an interesting question, because for anybody that knows the Dornier 228, it's gone through a large number of type certificate holders. From it's not owned by Dornier. It's been through Dornier to RAeS to now General Atomics. And they're a very small company, which is, I think, probably resourced not necessarily to support this kind of program. So parts availability, for example, is one of the problems that we come across operating an old aircraft. So there's challenges everywhere. But then we could buy a more expensive type that had a better and cheaper parts network.
Thank you.
Could you make some comment on the transient response characteristics of the fuel cell, or would you, because I believe they can be quite slow, or do you intend to manage that with your resistive load system?
What would you consider as the slow response rate?
Anything worse than a conventional gas turbine?
Yeah, so what would you consider to be certifiable time span from a flight idle power setting to maximum power?
I think you'd be looking around less than 10 seconds.
Yeah, so it's around 5 to 6 seconds. So because it's not certified, we don't need to meet that, but we actually do meet that. And the ramp rate that we can operate the fuel cells at is 33 Newton meters per second in terms of torque delivery. So it feels, from an operator's perspective, like a normal powertrain, and that can then be controlled through software. So you can move the power lever as fast as you like, and the ramp rate of the fuel cells comes up. But that sits within that what, as an operator, you would feel as that normal response time.
Thank you.
And there are plenty of older jet engines about that operate at a much slower time than that.
Sorry to add to that. Is that because of your batteries compensating?
No.
Okay, I think unfortunately we're going to have to pull stumps on it there time-wise, give these guys a little rest, time off for good behaviour and some good answers there. So I just want to thank them very much for a fascinating glimpse into the future of sustainable and more sustainable and more environmentally friendly aviation. So great lecture, thank you guys, very technical. Thank you also to the audience for some really good technical engaging questions that obviously stretch them but not beyond limits. So if you could join me both in terms of thanking the guys but also thank you and look forward to the next lecture.
Thank you.
Thank you.